Hey everybody, I want to show you how to make confidence intervals for the difference of two samples. So we're gonna talk about how to do that right now. So here is the key. The first key that we want to know is, in order to make our confidence intervals, we need to know what the sampling distribution of all the possible differences is. And this is what I was talking about in the last video. There I only talked about the difference between two means, right? That was the only one we covered. We're going to do two proportions here as well. So just a quick reminder, the difference between two means, and remember, so I'm assuming that this distribution is normal and this distribution is normal, right? So it's the distribution of sample means from set A, and this is the distribution of sample means from set B. And so we're just making the assumption that the central limit theorem applies here, right? Either the population is normally distributed or our sample was large enough, which is say 30 or more, that we are comfortable considering the sampling distribution normal. So this is a difference of two normal distributions, which is what the entire last video was about. And just to remind you, this is what we came up with here. So this is what we had for our sampling distribution. This is what we're going to be using for our confidence intervals for the difference between two means. This will be the sampling distribution that we want. Almost, right? We're actually going to turn these into S's and make a T distribution and all that, but for now, that's what we've got. I do want to talk about the difference of two proportions. We're going to do the same thing. So let me just remind you here of the basic idea. To find the mean of the difference of two normal distributions, you subtract the two means, right? So if I have X bar A minus X bar B, the distribution of all their differences is mu A minus mu B, right? And to find the standard deviation, what we did was we found the standard deviation of this thing and squared it, and the standard deviation of this thing and squared it, and added those together and square rooted the result. That's again from the last video. We're going to do exactly the same thing here. It's going to look a little different because the formulas for the standard deviation are different, but it's the same idea. So p hat, the sampling distribution of sample proportion, is this, right? We know this from the central limit theorem for proportions. So if I have the difference of two proportions, so if I have, like, let's call it P1 hat, I call the other one A and B, right? Well, whatever. P1 hat minus P2 hat, then that distribution is approximately normally distributed because, again, the P1 and P2 are normally distributed. So when you combine them, you get another normal distribution with a mean of, well, you subtract the means. So it's going to be P1 minus P2, P1 minus P2, and a standard error, standard deviation of this. So it's going to be the square root of each one of those things, square each of the standard deviations of P1 hat and P2 hat squared, and square root of all that. So it's going to be the squared. Actually, let me put the square root on at the end. So I'm going to have P1 times 1 minus P1 over N1, right? Because you could have different sample sizes. That whole thing is going to be squared. Excuse me, let's undo that, because it's not just that, it's the square root of this, and that whole thing is squared, which of course is just going to cancel. And then the second one is going to be P2 times 1 minus P2 over N2, square root of all that, and the whole thing is squared. Then we take the square root of the whole thing. Bit of a mess. So that's what the standard deviation looks like. Now, obviously, what's going to happen here is this squared is going to cancel with that square root, and this squared is going to cancel with this square root, and we're just going to be left with the stuff with no square roots on it inside. So that's N. So normal distribution with P1 minus P2. That was a little ugly. Let me undo that. P2. There we go. And square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. My handwriting, not the best as always, so sorry. Wish I could do this in Zoom, but I can't type it. So there you go. That's what we get for the sampling distribution of P1 hat minus P2 hat. And these are the sampling distributions that we're going to use in order to find our confidence intervals, right? In the same way that we used sampling distribution previously to find a, we used it for the standard error to find, how am I saying this? We use the standard error to find the margin of error by multiplying by the critical value, just like, that's what we did before. We're going to do exactly the same thing here. It's just that the standard error looks a little bit different. Instead of being this, now it's going to be this. So same idea, but different formula. We're going to take the standard error, we're going to multiply it by a critical value. The critical value is going to be determined because this is still a normal distribution. The critical value is going to be determined by the confidence level. And yeah, that's pretty much it. Other than that, it's pretty much the same. Our mean is going to be this guy. It's actually not going to be this, since we're going to be making confidence intervals. We don't have P1 or P2, right? Those are the things that we're estimating. We're just going to have hats on everything, right? It's going to be P1 hat minus P2 hat for the mean, and P1 hat times 1 minus P1 hat over N1, et cetera, et cetera. Right, so we're going to use hats instead of P's, and we have to meet the same requirements as before to use the central limit theorem, which is to say 5 successes and 5 failures in each case, right? So it has to be true for P1 hat and also for P2 hat. But you meet all the requirements of the central limit theorem. You substitute you put hats on everything. It's like it's the 1950s in here, right? Everything gets a hat. Yeah, and then you just make them in the same way. We'll do an example of each one of these in a little bit, but don't sweat it too much if it seems complicated now, because I think it won't be too bad. I'll try and explain it in the same sort of way. So I left myself another blank screen here because I want to do this. So for sampling distributions, the sampling what we're going to be using is this, and P1 hat minus P2 hat with, or excuse me, I'm not saying this very well. Let me back up a second, because this isn't exactly what I want to say. What I wanted to say was that for confidence intervals, so like if I'm trying to make a confidence interval, the thing I'm going to be doing is this. We're going to be doing P1 hat minus P2 hat, right? So that's our point estimate, because that's the thing we're making a confidence interval for, is the difference between the proportions. So our point estimate is the difference between the sample proportions, plus or minus our critical value, which we'll talk about in just a second. So that's going to be T alpha over 2 times our standard error, which is that big thing that we just had a second ago. So that's going to be P1, I think my picture's in the way here, P1 hat times 1 minus P1 hat or N1 plus P2 hat times 1 minus P2 hat over N2. And that's what we're going to do, right? So this is very similar to what we did before. So I don't think I have too much more I want to say. Let's just make some confidence intervals. I'm going to lead with the means. Oh, I want to talk about t distributions real quick, because we are going to use a t distribution for this. Let me go back to here. So notice this is a normal distribution, but of course it involves mu and sigma, and we're making a confidence interval. We don't have those things. Those are what we're trying to estimate, or probably mu we're trying to estimate. Or when I say it's mu, we're trying to estimate. That's not exactly true. We're trying to estimate the difference between the means. Right, that's the thing we care about. And by the way, that's how you can tell when you have a 2 sample test or confidence interval as opposed to 2 different 1 sample ones. If you're specifically comparing the samples to each other, as opposed to separately comparing them each to their own number. So here we're comparing them to each other. So I want to find I'm telling you how to do it when we're comparing to each other. And so we're going to want to find the difference between the means. That's the thing that we're estimating. If you think back to the last video when it was like difference between men's and women's heights, right? We weren't comparing the men's heights to a number or the women's heights to a number. We were comparing the men's heights to women's heights. So Like I was saying, it's unusual for us to know mu and or sigma, so we're going to need to approximate it with a t-distribution because we don't have a normal distribution here. So the thing to know, like I'm going to talk more about this when we get to the hypothesis testing video, because we're going to actually have to calculate our t-statistic in that case. It's a little bit messier, but it turns out to have much of the same idea as it does in the one sample case. So the formula is bigger, but the idea is the same. We'll talk about that then. For now, the only thing we really need to know is the degrees of freedom, because we need to be able to tell our calculator what the degrees of freedom are so that we can use inverse t, right? So it's going to be n-1, where n is the smaller of the two sample sizes. Now, that turns out to be a very conservative estimate of the degrees of freedom. Now, I don't want to go into too much detail. There's a formula in your book that is more accurate than this for the degrees of freedom. And the formula is a giant mess. It's like 4 layers of fraction. It's awful. And I never want to have you compute that by hand. You just don't have to. Your calculator or computer will do it for you, or I guess probably just the calculator in this case will do it for you. And you don't even have to worry about it. When we do this on the calculator, which I'm going to do after I do this by hand here, you'll see what it is. It's some fraction, which when you learn what degrees of freedom are, having fractional degrees of freedom is weird, because degrees of freedom are actually the dimension of a multidimensional vector space. So it's kind of strange to have a fraction or to have a non-integer, but it turns out through some fairly complicated math and taking a weighted average of the 2 degrees of freedom, you can get something more precise. And it also turns out that probably doesn't make any real difference. Like the thing I want to concentrate on is how to make a t-distribution for the difference between or how to make a confidence interval for the difference between 2 sample means. The general process, like having the most precise possible degrees of freedom, not relevant to the general process. And it's definitely not worth it to make you go through a giant calculation by hand to do. So I'm not going to. This, where this n-1, where n is the smaller of the 2 sample sizes, is a perfectly good way to do this. And if your sample sizes are close to each other, this isn't even that far off. And it's like the difference between the intervals is pretty minuscule. So I'm going to sacrifice a little bit of accuracy and precision in order to make it more understandable how to make them in the first place, which is really what I care about you learning anyway. So all that explanation aside, let's do one. So here's an example. We want to estimate the difference in average annual salary for UCSB students who graduate with a degree in biology versus a degree in communications. So we get salary data. Don't even worry about how we did it. Just assume it's a representative sample. Don't worry about the almost certain bias that we're going to get, right? Non-response bias and response bias and sampling bias. Ignore all of that. Just assume our data is great. So we obtained salary data for 33 recent UCSB biology grads and 38 communications graduates. The biology alumni have an average salary of this number with standard deviation of that. Communications alumni have an average salary of this with a standard deviation of this. And we're going to make a 95% confidence interval for the average difference between recent UCSB biology and communications graduates' salaries. Okay, so I want to do the thing that I recommended you do in hypothesis testing, which is read things twice and label stuff. So let's do that. So salary data for 33 recent UCSB biology grads and 38 communications grads. So I'm going to call this 33, I'm going to call this N sub B for sample size, but for biology students, right? So I'm going to call this right here N sub B, and you're going to have to bear with me with the writing. It's going to be really small here. 38 communications grads, so this is going to be N sub C. This is N sub C. Biology alumni have an average salary of 51,312. So this guy is going to be X bar B. Standard deviation of 6570. Now, again, with standard deviation, people often get this wrong. That's not population standard deviation. That's only referring to the sample. We have no parameters here. So this guy is SB. Communications alumni have an average salary of this number here. So that is X bar C. And a standard deviation of that. So this guy is SC. SC. We're getting 95% confidence interval. So there's my confidence level. Like it's another number that's relevant to me. for the average difference between recent UCSB biology and communications graduates' salaries. Okay, so let me go back a little bit here. So here is the sampling distribution for the difference between two normal sampling distributions, right? This is the distribution of all the possible differences. What we're going to do when we make our confidence interval is, oh, and I might need a little bit of extra blank page. Yeah, I didn't leave myself enough room here. What we're going to want to do for our confidence interval is the same thing, but we're going to substitute S's for sigmas, and our estimate of the difference between the means is going to be the difference between the sample means, right? The difference between the population means. Our estimate will be the difference between the sample means, just like when we were making confidence intervals to estimate the mean, we used the sample mean. So what I'm going to be doing here is this. I'm going to have, what did we say, biology minus communications. So XB B bar minus XC bar. That is my estimate for the difference between the population means, because it's the difference between our sample means, plus or minus our T critical value. What have I been calling it? I think I've been calling it TC rather than T alpha. TC times our standard error, which is this thing that we had before, but with S's instead of sigmas. So it's going to be SB squared over NB plus, oh man, SC squared over NC, right? And you might notice that that's what we had out here as our standard error, right? Same thing, it's just I've replaced sigmas with S's, and these guys are like, this is not the mean of my distribution because I don't know mu. I don't know either mu. All I know is the sample means, right? All I know is X bars. So this is the same idea that we had before. So I hope that's clear. If it's not clear, please come see me in office hours. I would be happy to explain it to you and compare in a little more detail here. But that's what I'm going to do. So I'm just going to take XB bar minus XC bar plus or minus critical value, which I still have to go find, right? So my degrees of freedom here, df equals, well, I'm going to use the conservative estimate of one less than the smaller sample size. So 33 was my smaller sample size. So I'm going to use 32 for my degrees of freedom. So let's go over to the calculator and find what that is. So I'm making a 95% confidence interval. So I want to do inverse T distributions, inverse T of 0.025 with 32 degrees of freedom. And the thing I get is negative 2.037. So that's my critical value there. And again, if it's not clear why that's the critical value, remember that what I've got here is, I'm trying to do this, right? I'm trying to get the 95% in the middle. That leaves me 2.5% on either side. And the thing that I just found here, this negative 2.037 minus 2.037, this is for T32, right? So if I go 2.037 standard errors away from the mean on either side of T32, that's what gets me 95% in the middle and 2.5% therefore on either side, right? Because there's 5% split in half on the outsides. So I've got 2.5% here, and so there is my critical value, 2.037. You can just drop the negative, it doesn't matter. You're going to do plus or minus anyway, so it doesn't matter whether you consider it positive or negative. It actually works fine either way. So I just always leave it positive. I think everybody always leaves it positive, to be honest. So that's what we're going to do here. We're going to, oh, I've got that already. So my degrees of freedom was 32. So I'm going to have XB bar, which I forgot its some number, 51312. So that's 51312 minus 48241. 48241. So that is my point estimate for the population difference between the two salaries. plus or minus 2.037. It was 2.037 times the square root of something pretty big. So we're going to have SB squared. So the standard deviation for biology was 6570. The other one was 10133. So we're going to have 6570 over 33 squared. No, other way around. 6570 squared over 33 plus 10,133 squared over 38. So there we go. Same thing as before. Point estimate plus or minus critical value times standard error, right? And that's how we're going to make all of our confidence intervals. So let's find all those numbers because I have no idea what any of them are. Share with the calculator. Calculator. Where are you at? There we go. 51,312. 1,312. Minus thing I've forgotten. Will it not show me? Where are we at? I have to whiteboard back to it. All right, fine. 51 minus 48,241. I should make these numbers more memorable in the future. Minus 48,241 is that number, so 3,071, and then we're going to do that minus 2.037 times the square root of 6570 squared over 33 plus 10,133 squared over 38. Bam. Minus 1,008.13, let's say. All right, so that's the low end. And then we're going to do that on the high end with a plus sign. All right, so same exact thing with a plus. Plus 3,071. What? No, oh, God. Sorry. Let me try that again. I don't want the answer. It was taking the answer plus the previous thing that I did. I want this to be 3,000. Oh, I need to insert here. Insert. 071. There we go. 3071 plus is what I'm trying to do here. It did answer. There we go. 7150 13. All right, so I've got negative 1,008.13 and 7150.13. So let's go put that here. Equals negative 1,008.13 up to 7150.13. Okay, so as we can see, this is a very wide range, and it's a very wide range because we don't have a very big sample. 30 people from each major is just not enough information to give us a very precise confidence interval. As you can see, we've got like an 8,000, we've got like an $8,000 range here for the difference between the two. And like, for instance, because of the uncertainty involved with the relatively large standard deviations that we have and the relatively small sample sizes, we think it is entirely reasonable that communications majors could, on average, make more than biology majors, right? Because we did biology minus communications, and we got a negative number for the bottom end, which is to say that communications is bigger than biology. And we got a positive number on top end saying biology is bigger than communications. So this number says that we think it's reasonable to think that biology majors make as much as $1,000, or excuse me, that communications majors make as much as $1,000 more than biology majors. And we also think that it's reasonable to think, based on our data, that biology majors make $7,000 more than communications majors. So we've got this really wide interval, right? So it's really important to get big sample sizes to get that down. This is not terribly precise, but it's all we can say based on the data that we've got. There's no way to make this better without taking a bigger sample. So that's it. That's pretty much what we're going to do here. Let me write my interpretation. Our data indicates that it's bigger, that the mean difference in salaries for recent UCSB biology and communications graduates is between, actually, I should say that we're 95% confident that, just to get the 95% in there, are 95% confident that the mean difference in salaries for recent UCSB biology communications graduates is between negative, how do I want to say this? I don't really want to say negative here. I really want to say between $1,008 greater, 13 more for grads, all the way to 7,150, 13 more for biology. Yeah, something like that, right? So I'm really just trying to get across the idea that at the bottom end here, we could have grads making up to $1,000 more than biology grads. And at the top end, we could have biology grads making up to $7,150 more than grads. And anything in there is reasonable as far as we're concerned, because we don't know where the difference lies, right? Like our data was $3,000 in favor of biology grads, but the uncertainty was so large that it extended all the way past zero to negative, to the negative side, and way up into the 7,000s on the positive side. So trying to provide a reasonable interpretation for this turns out to be really, really important. And I think I've said this, I don't know, 1,000 times so far, a lot. I'm going to say it again. Most people don't know what this interval means. And so as the person who has made the interval and understands what it means, it's your job to provide a reasonably understandable interpretation of it, so somebody doesn't have to know statistics in order to understand the point that you are trying to make. Like, you have to be able to communicate your point with someone who doesn't know all the background information that you know. So that's why this, right? So we're 90% confidence. No, oh my God, the typos. Confident. We're 95% confident that the mean difference in salaries for recent UCSB biology and communications grads is between $1,008.13 more for grads, all the way up to $7,150.13 more for biology grads. Difference in average salaries. Up to, should have the word average here. There we go. That's really important, because we are not talking about the salary of one individual person. We're talking about the overall average salary. And I need to state that in here just to be clear about that. Okay, I think I'm satisfied with this interpretation of the interval. So let's do a proportion interval, which is, oh, actually, before I do a proportion, we're gonna do it on the calculator. So let's go to the calculator. Where's the calculator? Because the calculator very conveniently has a 2-sample t interval. Stat tests 2-sample t interval. There's a z interval. We're not using that one because we don't know sigma. 2-sample t interval. This is the one we want. And notice that, again, data or stats, we don't have the raw data. I didn't give you like a list of 33 biology salaries and 38 communication salaries. Instead, we have summary statistics. And lo and behold, they're asking for the same exact things that I wanted to know, unsurprisingly. So X1 bar, I'm going to have 1B biology and 2B communications. I think that's I think they're going to do 1 minus 2 here. I'm not actually sure. X1 bar was something. I've forgotten the number. 51,312, 48,241. Okay. 51,312. Can I go down to 48,241? Okay, there we go. And we're going to talk about pooled in just a second. S1 was 6570 and N1 was 33. S2 was 10,130. I don't know why I can remember these numbers. And N2 was 38, confidence level 95%. And now let's talk about pooled. So just like the TLDR version of this is leave pooled on no. There you go. Now let me explain why. So what pooled is if you can make the assumption that S1 and S2 are two samples from populations with the same standard deviation, and therefore their population standard deviations are equal, well, then it turns out you can do some fancy stuff and get an interval that is very, very, very marginally more precise. And I mean, the difference is really small. And that's what pooled is asking. They're saying they're asking, can we pool these two standard deviations together to get a slightly more accurate version of the standard deviation and therefore be slightly more precise with our interval? The answer here is just in principle, no, because there's no reason for us to think the standard deviations of salaries for communications and biology grads are the same. So another reason why we wouldn't pool them is these things are not very close together. So we don't necessarily think that they're two smaller samples from a larger population with the same standard deviation. And the third, there is another hypothesis test you can do that we will actually learn to determine if it's reasonable to make that assumption. We haven't talked about that assumption. We haven't talked about that hypothesis test yet. We will when we get to ANOVA. So for now, just leave pooled on no. That's the upshot of this. Calculate. Oh, they got a slightly different confidence interval than us. And the reason they did, notice their degrees of freedom, right? I used 32 degrees of freedom. They're using 64.1195, this fractional number or this decimal number of degrees of freedom, using that formula I was talking about. You can see it in your book. I should find the page. I'll show you the page if you're interested. It's big and messy. We don't have to use it. And that is what's making their interval more precise than mine, right? So the interval I made went from 1,008 down to, or 1,008 up to 7,150, or negative 1,008 up to 7,150, and there's, right, the negative 1,008 moved in a little bit to negative 929, and the 7,150 moved in a little bit to 7,071. And so they have a slightly better interval, right? They went $79 in on either side, which is nice. That extra precision is great. It's not worth that. It's not worth the extra hassle of calculating this, in my opinion, at least not by hand. Yeah, so that's why the interval is different. Is it's the degrees of freedom. It's not that the pooled versus not pooled thing. That's irrelevant. In fact, I did it with pooled no. I'm gonna turn on pooled yes, and just to show you how negligible of a difference it is. So let's do that again real quick. So stat tests, that one, two sample T. We'll use pooled yes. Calculate. What? Why did it get worse? What on earth? Hang on. I've literally never seen that happen before and don't know how it's possible. That pooled yes. I'm genuinely stumped. Just leave pooled off. Leave pooled on. No, I cannot explain this. I have never seen that get less precise by turning pooled on before. That's really weird. Okay, anyway, don't turn pooled on. Just leave it off. That if you try this on any other problem, you're going to find that it's slightly more precise. That's really weird. Okay, ignoring pooled, just leave it on no. That's all I really want to say about this. If you want to use this to make your intervals, go right ahead. I'm not really expecting you to do it all by hand, right? You can do all this stuff if you want to. If I was just making an interval for me, I certainly wouldn't. I would just use the two sample T interval because it's so much easier. And it's also more precise than doing it by hand. But I did want to show you, like the whole point of this was to show you that we really are just doing the same thing as we were in the one sample case, and the confidence interval has pretty much the same interpretation, right? The parameter we're trying to estimate is the difference between two parameters, right? So we're trying to estimate the difference between mu biology and mu communications. So we use X bar biology and X bar communications to center our interval. And we use the sampling distribution for all the differences, which is this thing. This is the unpooled one, by the way. This is the formula you use for unpooled. Pooled does something different that I'm not going to get into. Yeah, there you go. Oh, and then this is the reason why our interval was a little bit bigger than theirs, was because we used 32 degrees of freedom. We could have done, they had like 64.1159 degrees of freedom. And then that would make this number a little bit smaller, which is why this interval is smaller. That's the only difference there. Okay, I think I've rambled enough. I feel like I'm rambling too much. In fact, let's move on to the next example, which is difference of two proportions. All right, so here we want to estimate the difference of two proportions. So let's read twice. We want to investigate whether pet ownership is related to unemployment. So the theory goes that unemployed people will often get pets to keep them company at home, and that they have more time to take care of a pet than people with full-time jobs, which is perfectly reasonable. So we take a survey and find that of the 117 pet owners in our survey, 62 have full-time jobs. Of the 96 non-pet owners in our survey, 61 have full-time jobs. So we're going to make a 90% confidence interval for the difference in employment rate between pet owners and non-pet owners. So again, we're not saying that pet ownership causes unemployment or employment, or vice versa, or that unemployment causes people to own pets, even though that's kind of what the theory is. We're not actually making any sort of distinction, or we're not making any claim to to explain the cause of any relationship that might or might not exist. We're just trying to determine if there's a relationship or not. So that's what we're going to do. We're going to estimate the population proportion, or the difference between proportion of employed pet owners and proportion of employed non-pet owners, or unemployed. Same deal, just the other way around for unemployment. So let's go see what our distribution is going to look like. It's going to be this, right? So we're going to be using this sampling distribution here that I've helpfully marked up in pink and crossed things off of. But that's the one that we're going to be using. We're trying to estimate P1 minus P2. And so we're going to be using P1 hat minus P2 hat to estimate that. And then our standard error looks like this, except everything has hats on it because we're using sample data instead of population data. And that, in this case, doesn't change it to a t-distribution. It still leaves it as a normal distribution for reasons that I do not want to take time to explain. Oh, I'm sorry. I called this, I think your book calls this T alpha over 2. I've been calling it TC in this class. Let me fix that. There we go. Same thing, just different labeling. There's all kinds of different. Some people call it like T star or T alpha or T alpha over 2 or TC. I've seen all of them. So we've been using TC. I'll just continue doing that. C for critical value. So 1 and 2 in my cases are going to be people employed and unemployed. So let's go ahead and read this again to make sure that we've got all the detail here. So there's a theory. I think we can start here. We take a survey and find that of the 117 pet owners in our survey. So we're going to call that something with a P for pet owners and then N for non-pet owners. So of the 117 pet owners, so this is N sub P, right? That's the number of pet owners in our survey. 62 have full-time jobs. So that is, depending on how we want to do this, what would we say? Ownership is related to unemployment. So let's do this for unemployment, right? So 62 have full-time jobs. So then I'm gonna call this X sub P, but that's not quite right because I'm actually going to use 117 minus 62. I'm going to use 55 for the unemployed people, right? I'm trying to determine if pet ownership is related to unemployment. Now you could certainly use 62 as X sub P if you wanted to, and then you're just investigating whether pet ownership is related to employment, which is pretty clearly the opposite of unemployment. So yeah, either way. So this is not quite X sub P, it's a little question mark. Of the 96 non-pet owners, so this guy is going to be N sub N, and so sample size of non-pet owners. 61 have full-time jobs, so this guy is going to be also not quite X sub n, question mark, make a 90% confidence interval. So I'm actually going to do X sub P equals 117 minus 62. So the unemployed half, or the unemployed portion of our sample. So that's 55. And then X sub n is going to be 96 minus 61, which is 35. All right. Now, theory goes that unemployed people will often get pets to keep them company at home, and that they have more time to take care of a pet than people with full-time jobs. So the theory here is that unemployed people would be more likely to have pets than people with full-time jobs. So I'm going to do non-pet owners minus pet owners. So I'm going to have n equals 1, and p equals 2. Where the 1 and 2 are referring to the subscripts in the formula that I'm going to use, this formula here, right? So I'm going to do non-pet owners minus pet owners, just so the expected number comes out to be positive here. All right, let's see how that turns out. So I'm going to do, let's write this down. We're going to do P, that's still pink. I kind of want this one to be blue. I like pink for my marking up. We got P, so non-pet owners, Pn hat minus P sub P hat. And we're going to do that plus or minus T sub critical, not T critical value. Did I say T? Oh man, I bet I have that as T on the other one too. This is a Z critical value. I think I wrote it wrong. All right, I'm not going back to reshoot this whole video. I'm just going to go fix this here. And I hope everybody's watching to this point so they can see me fix my mistake. Oh man, Z sub Z. Because I want to use a normal distribution for this. So I need the critical value coming from a normal distribution. And I wrote T because I'm so in the habit of doing things with T's. So Z sub C times square root of, I'll put the hat on this, or the top on in a second. We're going to have P sub n hat times 1 minus Pn hat over n sub n plus P sub P. I have so many of the same letters in this problem. This is ridiculous. 1 minus P sub P hat over n sub P lid. All right, so we're gonna do that. So let's find those things. I need to find P sub n hat and P sub P hat. I need to make this actually look at least vaguely like an N. And there we go. All right, so we need to find Pn hat and P sub P hat. So we get Pn hat equals, so the non-pet owners, we had 60 or 35 out of 96. 35 out of 96, which I think I'm going to show you guys a trick that we can use to put this into the calculator a little bit easier. It's not a super important trick because we're going to do this by, getting the 2 prop Z interval eventually. But I do want to show you a trick because it's a nice trick in your calculator that you may or may not be aware of. And then we're going to have P sub P hat is, what was it, 55? 55 out of 117. I think that was the right number. 55 out of 117. Yeah, that was right. Okay, good. All right, so here's what I'm going to do. I'm going to jam this all in the calculator right now. It's going to be kind of a big mess, but I can make it a little bit less of a mess by doing the following thing. All right, you ready for this trick? Your calculator will store constants into variables, so you don't have to type them in all the time. So what I'm going to do is I'm going to do 35 out of 96. And instead of hitting equals here, I'm going to hit store. And this is my non-pet owners, so I'm going to store this to n. So you can see the letter keys on the calculator here, right? So A, B, C, D, etc. I'm going to store this one into N for non-pet owners. So the way you get the greens here is with the alpha key. So alpha N. So 35 over 96 is going to go into N, and then so N is going to be 0.364. And now if I just do N, it will be that number, right? So I can just put in N rather than having to type in 0.3645833 or 35 out of 96. So the other one, we're going to have 55 over 117. I'm going to store that into P for pet owners. So that's alpha P. And so the things that I'm going to do in the formula, I'm just going to have N's and P's, right? And we're going to do non-pet owners minus pet owners. So I'm going to start with parentheses non-pet owner N minus P minus, I forgot to calculate our T critical value. I need to get rid of all this. Sorry. I forgot to calculate our T critical value because I know it off the top of my head, and you guys probably don't yet. So let's do inverse norm, right? So let me go back briefly because I think I'm maybe making this a little scattershot here and hard to follow. Who would have thought? 90% confidence interval. So I need to do 90% in the middle, 5% on each side, right? Because there's 10% total that gets split in half. Outside what I want. So I want to do inverse norm of 5% with a mean of 0 and standard deviation of 1. And we will see what that is. Now, you guys might or might not know this off the top of your head. It's a fairly common number in statistics that we've used a couple times. And if you've had stats before, you probably remember. Area is 0.05, mu 0, sigma 1, tail off is fine, and we get 1.645. Yeah. So negative 1.645 is my critical value. That's my Z sub C. Or excuse me, positive 1.645 is the critical value. Again, you can use positive or negative. It really makes no difference. The calculations come out the same. So what I've got here, I guess I will I'll write it in here. So I'm going to have. Do I do that? No, I just want to do this, just for concision. 1.645 is the one I'm going to use there. Okay, now let's actually go to the calculator and do this. We're going to do N minus P, right? In the calculator, N minus P plus or minus 1.645 times the square root of all that nonsense. So let's go do that. Calculator. So we're going to do N minus P. Nope. N minus P. So alpha N minus alpha P. I'm going to go ahead and put some parentheses around this. I don't think it's necessary, but just to be safe, we do that minus 1.645 times the square root of a whole bunch of stuff. So it's going to be n times 1 minus n. So alpha n times 1 minus n, 1 minus alpha n, all over n sub n, which was 96, plus p, so alpha p, times 1 minus alpha p, all over n sub p, which was 117. We get that number, and then we do the same thing again, but with plus. There we go. So we have a difference of 21.6% on the low end and 0.5% on the high end. So let's go write that down and talk about what that means. So this is we say negative 21.6% up to 0.5%. Make sure I remember that correctly. I'm doubting myself on that second number. No, that's right, 0.5%, 21.6. Okay, so that's fine. So when we took away unemployed minus, or we took away unemployed pet owners minus unemployed non-pet owners, we were thinking, so our theory went that with the extra time at home and need for more company, that unemployed people would have a higher proportion of pet ownership. That's not what our data found. I don't know. I assume some of you probably noticed this already, that 62 out of 170, or excuse me, that 55 out of 117 is a bigger ratio than 35 out of 96, right? When we calculated P and N, that's, what am I trying to say here? No, other way around. Losing my train of thought here. So pet owners have a higher proportion of unemployment. No, that's, what did I do wrong? Oh my God, my brain is all over the place here. The unemployed proportion of non-pet, oh, right. Non-pet, oh, I'm getting it backwards. I'm sorry. These are pet owners. Or yes, these are the pet owners. So our pet owners have a higher proportion of unemployment than our non-pet owners, right? So our non-pet owners are more likely to be employed is the idea, right? So when we did non-pet owners here and pet, do I have this backwards? Do I have this backwards? I'm gonna have to reshoot this video, I hope not. 117 pet owners, 62 have full-time jobs, and 55 don't. So XP is 55 or 117, which is about 47%. That's a higher rate of unemployment than the non-pet owners. Right. That's opposite of what our theory is, right? Our theory says that non-pet owners would have a higher rate of unemployment than our pet owners, which is backwards. So sorry for the stumbling all over myself here. This came out exactly like I wanted it to. Sometimes, because I want to make the point here that sometimes our expectations, sometimes the data is the opposite of what our expectations are, right? So this theory goes that unemployed people will often get pets. So we're expecting pet owners to have a higher rate of unemployment. And they don't. In our survey, the pet owners had a lower rate of unemployment. Okay? And so, yeah, so the pet owners had the non-pet owners had a lower rate of unemployment, which is the opposite of what our theory predicts. Sometimes that happens. In fact, that happens significantly more often than you might imagine when you're doing actual statistical research. And that's what's happened here, according to this data that I totally made up to make this point, is that this negative number, when we did non-pet owner unemployment minus pet owner unemployment, we get a negative number, meaning that pet owner unemployment is bigger. Wait, do I have this backwards? No, I have this right. Non-pet owner unemployment. We were thinking that non-pet owner unemployment would be. I'm just gonna have to reshoot this whole thing. This is terrible. Pet owners have a higher rate of employment than non-pet owners. All right. Anyway, I'm probably just going to keep this in. I don't really want to shoot another hour-long video. So I guess this actually goes with our theory that non-pet owner unemployment is no non-pet owner. This is unemployment. Pet owner unemployment rate is higher than non-pet owner. Yes. Sorry. Try not to do this again. Anyway, let me conclude. Let me make a reasonable conclusion for this. So we're 90% confident that the difference in unemployment rate between non-pet owners and pet owners is between these two values, 21.6, negative 21.6%, 0.5% when we do non-pet owners minus pet owners. So this is pet owner unemployment rate, or this is the pet owner unemployment rate is bigger, And this is the non-pet owner unemployment rate. It's bigger because we did N minus P. So let me get that down here. So we are 90% confidence that the difference between unemployment rates of pet owners and non-pet owners is between 21.6% higher for pet owners and 0.5% higher for non-pet owners. And yes, I know you can't see that right now. There we go. So there's my conclusion, right? That's what this says. Since we did N minus P, when we get a negative number, that means P was bigger. When we get a positive number, that means N was bigger. So our estimates for proportion for population unemployment rate among non-pet owners minus pet owners is between 21.6% and 5%, where 21.6% is pet ownership or pet owners unemployment rate is higher, and then the 5% is when non-pet owners unemployment rate is higher. In fact, I think I did my subtraction backwards because the idea was to do this the other way around. All right. So if that explanation was in any way helpful to you, that would be fantastic. I feel like I said so many wrong things that it's going to end up being confusing, but the thing you want to concentrate on is this. This number right here is our estimate of the difference in unemployment rates between non-pet owners and pet owners. That difference, we are 90% confident that difference is between here and here. That's the idea you want to get across. So that's the idea I have attempted to get across rather awkwardly. Sorry. I think the problem was that I tried to make something happen and then did it wrong here. I should have been doing pet owners minus non-pet owners and ended up with positive numbers, but I meant to anyway. Forgetting all that, let's do it on the calculator because that'll be a lot smoother. I'm hoping. Gosh, I hope it'll be a lot smoother. All right, so let's go back and remind ourselves of the important things here. So I'm going to do it the same way, even though I think that's backwards what I actually wanted. We're going to do non-pet owners minus pet owners. And so that means non-pet owners are going to be 1 and pet owners are going to be 2. So our N1 is going to be 96. Wait, did I say non-pet owners minus? Yes. N1 is going to be 96 and X1 is going to be 35. N2 is going to be 117 and X2 is going to be 55. So 35 and 55. All right, let's go to the calculator. So we're going to look in the same place, not there. We're going to look here instead. Tests, we want to do a 2-prop Z interval. So that's down here, 2-prop Z interval. So 2 proportions making a Z interval. X1 was 55, no, it was 35, and N1 was 96, and X2 was 55, and N2 was 117. And we're making a 90% confidence interval. This one's going to come out to be pretty much the same as what we found, I hope. Yeah, you can see it's the same as what we found, right? So there's no like weird degrees of freedom calculations to get. But yeah, there you go. That's the same interval we got. As you can imagine, this is the easy way to do it, and I would recommend you do that. And when you're trying to figure out what to show on your on a test or homework assignment or whatever, the thing I would want to see is something like 2-prop Z interval on the calculator with X1 equals this, N1 equals that, X2 equals this, N2 equals that, and confidence levels. Like, so just basically write down this screen so I can see what you're doing. And if there are some numbers that need explaining, like why 35 instead of 61, right? I thought it was 61 employed people. It is 61 employed people, but it's 61 employed people, and we're trying to do unemployed. So we're doing 35 out of 96 here. Yeah, so that's the idea. So make sure you put this in, and the way this works, the reason this all works is because of this sampling distribution that we've done here, right? So this is what your calculator is doing, and you can see that this is in fact what they were doing because we got the same interval as the calculator did when I did it over here and then explained it really badly. But that's like, this is the thing I did, and this is what the calculator is doing as well. So I think that's kind of where I want to leave this. I think maybe I would have liked to leave it without all the confusing explanation, but you know, what are you gonna do? So yeah, again, if you have any questions, please come see me in office hours. I promise I will be more helpful there than I am in the video. And I'll just leave it at that and say that is enough for now. And I will see you guys in the next video.